Hello students, today some more problems on subspaces. Let W is the union of first and third quadrants in x and y. So we are taking one vector xy where whose product is always positive in the sense if it is in the first quadrant then both are positive, that's why positive into positive is positive. In the same way in the third quadrant means both are negative, right? So negative into negative is also positive, so it means it is in either in first quadrant or in third quadrant. Then is cu in w and y, so then scalar multiplication is possible or not, let us check. So given that R2 is a vector space because it has two entries, so R2 is a vector space and it is in either first or third quadrant whose product is always positive. So to check scalar multiplication, Cu belongs to W or not. Suppose we are taking in the first quadrant. Suppose in the first quadrant, take any scalar C first. If it is positive, what will happen? If it is negative, what will happen? Let us see. For any positive number, suppose I am taking 2 here, then 2 into first quadrant element means both are positive, x comma y. So you can take like this. Then positive number into 2 is again positive number. So positive into positive means always greater than 0. So here in first quadrant, suppose you are taking any positive number, so it is belongs to W. In the same way, suppose C is any negative number, then multiplying these two, then both are negative in the sense it may be in the third quadrant. It should be in the third quadrant. So obviously that product is positive. So by taking any positive scalar or negative scalar in the first quadrant, then it is belongs to W. Similarly, in the third quadrant, suppose take any positive number for C, then positive into both are negative in the third quadrant, so you can get negative numbers whose product is positive. So obviously it is belongs to W. In the same way, if it is negative also, what will happen? Minus into minus plus plus. Then this vector is in the first quadrant. What we have here, it is either in the first quadrant or in the third quadrant. So it is also possible for C is positive number or negative number. So from 1 and 2, what we can conclude? Cu is belongs to W for any scalar. Either it is positive or negative for U belongs to W. So see another problem. Here V is given which is only in the first quadrant. Only in the first quadrant means X is positive, Y is positive. Like this is first quadrant means X is positive, Y is positive. Then is vector addition is true or not? I mean, is vector addition exist or not? And is scalar multiplication is not possible. So U plus V is in Y, but C into U does not belongs to V, that we have to prove. So R2 is a vector space because it has two entries. So V is in the first quadrant. So by definition we are writing like this. To prove U plus V belongs to V, take U belongs to V. U belongs to V means you take any number in V, that is some x1, y1 where x is greater than 0, y is greater than 0. So y1 is greater than 0. Similarly take V. V is some x2, y2 where x2 greater than 0, y2 greater than 0. Now take U plus V. Then when you are adding x1 plus x2 which is also positive and this is also positive. So obviously this is belongs to what? V. Therefore U plus V belongs to V. So vector addition has proved. Suppose by checking the scalar multiplication, suppose when you are taking any positive number, so it is in the first quadrant obviously, but C is any scalar in the sense it may be negative number. Suppose I am taking here negative number, what will happen? Minus 1 into first quadrant element is, suppose I am taking some x and y, or we can take some 2 and 3. Then when you are multiplying, what will happen? Minus 2, minus 3. But obviously they are not positive numbers, but according to the condition of first quadrant, they must be positive number, but here there are no positive numbers, so it does not belongs to V according to the given condition. So Cu does not belongs to V for not every scalar. So this is one kind of different problem. For what values of H will Y be a subspace of R3 which is spanned by V1, V2, V3? Here 3 vectors are given and suppose it is spanned by R3, then what will be the value for H? It is asking. So in the Y, one variable is not given, one element is not given. If it is spanned by these 3 vectors, then find the value of H, it is asking. So given vectors and given Y, and what is given here? Y is it is spanned by these 3 vectors, in the sense what we can write? It can be expressed as linear combination of these 3 vectors. What is meant by linear combination means, for 3 vectors we are choosing three scalars such that we can write y as a1 v1 plus a2 v2 plus a3 v3. We can choose any scalars like s1 s2 s3 also. So substitute y these all values. Now this is nothing but the system of linear equation with three unknowns, isn't it? Suppose when you are writing in the equation form, what will happen? A1 plus 5a2 minus 3a3 equal to minus 4. Like that we are having three equations with the three unknowns. So by solving three equation with three unknowns means how you can find? Simply by solving that equation, that is one of the method, and another one is we can converting into augmented matrix form and do the row operation. So take the first column in first matrix, first column, second column, third column, take it as it is, and what will be the right side of the equation? Suppose when you are taking as the equation, what will happen? A1 plus 5a2 minus 3a3 equal to minus 4. So that column we are taking here. Now by doing row operations, how many possibility? I mean, you have to find out the rank of this augmented matrix, and if it is consistent, if and only if rank of augmented matrix is equal to rank of A. So for that we are taking the row operations, like this must be converting into 0, right? So for that, to make it into 0, R2 plus R1, then it will be 0. So take R2 implies R2 plus R1. Here minus 2, here 1. So R3 plus 2 into R1, then it will be 0. That's why we are taking here. So R1, R2 plus R1 means 0. R2 plus R1 minus 4 plus 5. 1, 1 minus 3, minus 2, like that we can do for everyone. Similarly for R3 plus 2R1. R3 plus 2 into 1, 2. Minus 2 plus 2 is 0. Similarly R3 plus 2 into R1, 10 minus 7, 3. Like that we can do. Here R3 plus 2 into this means minus 8. So H minus 8 or minus 8 plus H. Now here it is also, we can converting into 0 by taking what? R3 minus 3R2. So see here R3 minus 3R2, then it will be 0. It will be 0. R3 minus 3 means minus into minus plus 3. 3 minus 8 is minus 5. So H minus 5. Now here this is the augmented matrix. So our condition is rank of A. A means only up to here, and rank of augmented matrix means this total. So rank of this A in the sense number of non-zero rows. How many non-zero rows here? 1, 2. This is 0 row. So rank of this matrix is 2. And here rank of this augmented matrix means number of non-zero rows in this total is 1, 2. Here it is non-zero, so 3. But we want rank of A equal to rank of this total augmented matrix. When it is possible, if this value is 0, then only these ranks are equal. So when it is 0, rank of A be equal to rank of A means H minus 5 must be 0, so H is 5. So if y can be expressed as linear combination of the given three vectors, then what will be the value for H? 5. Now today we will discuss some more topic, homogeneous linear equation. A system of linear equation is said to be homogeneous if it can be written in the form of Ax equal to 0 bar. Suppose here non-zero vector is given, this is called non-homogeneous linear equation. Suppose here 0 vector, then we can say it is homogeneous linear equation. So it is in the form like Ax equal to 0 bar. We know obviously when you are taking any matrix multiplied with 0, then obviously 0 will come. So for every this linear equation, homogeneous equation, it must have one solution, that is what? X equal to 0 bar. When you are taking here 0 bar, then obviously 0 bar. So this type of solution is said to be trivial solution. So for every linear homogeneous equation, we must have at least one solution that is trivial, and other than this trivial, we have non-trivial solutions also where this x is not equal to 0. If it is possible, when if it has at least one free variable, then non-trivial solutions will come. Now let us discuss the null space of a matrix. The null space of M cross N matrix A is the set of all linear solutions of the equation Ax equal to 0. Suppose, and it is denoted by null A, that means what? We have to take some vector x which is belongs to R power n. Suppose A is of M cross N matrix, then n is nothing but number of columns in the matrix. Now x must be belongs to Rn, means x should have number of entries n, where which is the column of A matrix. So, and also it should be proved that condition as Ax equal to 0 bar, means any vector which is belongs to null A, in the sense that vector belongs to R power n, at the same time Ax equal to 0 bar. This is the condition for null A. And we know that null A is also a subspace of vectors. Null A of matrix A is also a vector space, and it is a subspace of R power n because it is belongs to R power n. So, see here some problems. One matrix is given here and one vector is given. Determine U belongs to null A or not. See, A has 2 rows, 3 columns. So, it is of 2 cross 3 matrix. U means 3 cross 1 matrix. So, to check U belongs to null A, what is the definition for null A? It must be X must be belongs to R power n, at the same time Ax must be equal to 0 bar. So, here what is a vector space here? R power n. What is n here? Number of columns are 3. So, obviously R3 is a vector space. And is U belongs to R power 3 or not? Yes. Given U is what? This one. So, it has 3 entries. So, it is obviously belongs to R power 3. So, first condition is proved. So, similarly, what is the second condition? AU must be 0 bar. So, consider AU. A into U. Here, when the product of two matrices is possible, in the sense number of columns in the first set is equal to number of rows in the second set, then only we can do the product, and the resultant value will be 2 cross 1 matrix. So, see here A into U. Now, first row into first column, then first row first column element, like 1 into 5, 5 minus 9 plus 4 here. Second row first column means second row first column element, that is minus 25, 27 minus 2. Then 9 minus 9 0. Here 27 minus 27 is 0. See, 0 bar. So, here U is belongs to R power 3 and also A into U equal to 0 bar. So, from this definition of null A, what we can conclude U belongs to null A. So, see another problem. W is given, A is given, determine W is in null A. So, here what are given, that we have to write first. To check W belongs to null A, first write the definition of null A. Say Ax equal to 0 bar and X belongs to R power n. So, here it has 3 entries. So, R3 is a vector space and it is belongs to R3. So, second condition is A into W. Here it is given W, that's why A into W means A into W. First row into first column, 3 minus 15 plus 12. Like this, second row first column this is, and third row into first column. So, here 15 minus 15 0, 0 and 12 minus 12 0. So, here also A into W equal to 0 bar. So, W belongs to null A. Similarly, we can do W A are given. To check the same process, write the definition. So, W is obviously it has 3 entries which is equal to the number of columns. So, it is belongs to R3. Also, A into W, when you are taking first row into column, second row into column, third row into column, then, so see here, first row first column, second row second column, third row third column, then 0. So, W belongs to R3, AW equal to 0 bar, so W belongs to null A by definition. Now, here is one theorem. Show that the null space of M cross N matrix A is a subspace of R power n. So, already we have discussed that null space is obviously a subspace of R power number of columns here. Let us see. A is of M cross N matrix, suppose, means with M rows and N columns, and R power n is a vector space. By definition of null A, what we can write? X is in R power n and Ax equal to 0 bar. Then to prove null A is a subspace of R power n, obviously these elements are belongs to R power n, so it is a non-empty subset of R power n. So, it is enough to prove for subspace 3 conditions, like 0 bar belongs to subspace. What is subspace here? Null A. So, 0 bar belongs to null A in the sense 0 bar must be having n number of entries, right? So, 0 bar we can write it as 0 0 0 like up to n times, 0 n times, right? So, it is obviously belongs to what? R power n, and also we have the condition it belongs to R power n, and also Ax equal to 0 bar. Anything, obviously A matrix A into 0 vector is obviously 0 vector, right? So, it is belongs to R power n and A 0 bar equal to 0 bar. So, 0 bar is belongs to null A. Similarly, we can prove vector addition. That is what, take two elements from null A, then u plus v belongs to null A. To check this, u belongs to null A in the sense u must be belongs to r power n, and also a into u equal to 0 bar. According to the definition, we can write similarly for v. See here, then u plus v belong, what is that? U belongs to r power n, v belongs to r power n. Then obviously u plus v is also belongs to r power n. And also u plus v belongs to null space of A means, first of all u plus v belongs to r power n, and a into that u plus v is also equal to 0 bar. So let us consider a into u plus v, then we can multiply as au plus av, right? So au equal to 0 bar according to the, see here, AU is 0 bar and AV is 0 bar, then substitute there. See here, 0 bar plus 0 bar is 0 bar. So U plus V is belongs to R power n, and A into U plus V is 0 bar. So U plus V belongs to null A according to the definition. Similarly, scalar multiplication. C is any scalar, U belongs to null A in the sense condition. So C into U means, C into U belongs to null A in the sense CU must be belongs to R power n first of all. So C belongs to R, U belongs to R power n means obviously CU belongs to R power n, and also A into CU must be 0 vector. So A into CU can be written as C into AU, but according to the null space definition, AU equal to 0 bar, so it is 0 bar. So here what happened? CU belongs to R power n, and also A into CU is 0 vector. So this CU is belongs to null A. So from 1, 2, 3, it has proved three conditions. So null A is a subspace of R power n. So tomorrow in the next video, we will discuss some more problems on linear combination. Thanks for watching.